Okay. So first of all, so let's start with easy questions. So first, easy question. Suppose you have a function f of x equals 3. So what does that graph look like? What kind of line? It's a horizontal line. So if I say, what's the area under this function from x equals 1 to x equals 6, this is a trivial question. Because what's that shape? It's going to be, well, a rectangle. But exactly. So, well, yeah, okay, great. It's a rectangle. So we know the area is simply the height, which is 3, times the width, goes from 1 to 6, so the width is 5. So the area is just 15. Easy, done. Okay, let's kick it up a small notch. What's the area under this function, f of x equals 3x, between x equals 0 and x equals 4? Okay, so here's that. What shape is this going to be? This is a triangle. Great, because we know how to find the area of a triangle. It's just half times base times height. So in this case, the base, since we're going from 0 to 4, the base is going to be 4. And then what's the height? The height, exactly, the height is going to be f of 4, which is 12. So you just get half times 4 times 12, work it out in your head, you get 24. Great. So as long as I'm asking you to find the area of a shape that we know, super. What about? What's the area under this function, f of x equals x squared, between x equals 1 and x equals 3? So this is not easy at all, right? This is clearly not a shape that we know because the graph is curvy. All right. So how can we think about finding this area? We're going to, if it's a parabola, where are the triangles?
You're asking the exact area or just approximately?
Well, that's a good idea. Can we? Okay, so what if you wanted to find the exact area, or what if you wanted to approximate it? How would you do either of those
If
things?
you want to approximate, then you do different shapes inside the whatever area you want to find. And if you want to find the exact area, you have to do a fundamental area calculus.
Okay, oh, so you already know this. Okay.
Well, he said
All right.
different shapes. Shouldn't you use the same
shape.
Okay.
Yeah, it's the
Right.
same shape,
So,
different sizes.
right. So the way that we're going to approach this question is we're going to start by saying, well, this is something we can do exactly, so let's try to approximate it. So if you're going to try to approximate an area, you're going to want to use shapes that you know the area of. So what's the most basic shape that we know the area of?
Rectangle.
Rectangles. That's our fundamental way of thinking about area. So we're going to do our best to approximate the area of this graph using rectangles. Okay. So here's the graph, and what I said was going from x equals 1 to x equals 3. So let's make rectangles. So how are we going to make rectangles that approximate? Okay, that's the area. How do we make rectangles to approximate that?
Come up with an interval, and then we make rectangles out of that interval.
Right. So the worst way to do this, or the most simple-minded way to do this, would just be, let's make one rectangle and hope for the best. Okay. Now, what we've seen is that obviously that's not a good idea. Okay. So what are we going to do? We're going to make a bunch of rectangles. All right. So in order to keep the math relatively easy, okay. So where are we going to put these rectangles? Let me ask you that.
There are two ways. Well, there are two different ways.
Okay. Right. So where's the bottom of the rectangle going to be? Yeah. We're going to want the rectangle bottoms to be down here somewhere. Okay. And where should the top of the rectangle be?
At the point of height.
Yeah, it should be, the top of the rectangle should be on the function somewhere. So for example, we're going to make, let's see. So how many rectangles should we use? Let's use 2. Great. So one rectangle is going to go from 1 to 2, other rectangle will go from 2 to 3. That's fine. So this first rectangle, how high should it be? Where should it stop? It should stop at the curve. Okay, now of course the whole problem is where on the curve means, I mean, from 1 to 2, it could be anywhere from here up to here. So we could draw this rectangle, we could draw this rectangle, we could say, hey, let's draw that rectangle. So there are any number of rectangles that we could use for our approximation. Okay. So now, and of course you can do the same thing from 2 to 3. So now that we've agreed upon that, great. That takes us to the next place. Whoa. Okay. So now, in order to make the mathematics simple, I'm going to make some simplifying assumptions. So here's the first thing. The first thing is, so we're going to use rectangles. So the first thing is we're going to make each section, or in other words, each rectangle width, exactly the same. That just makes sense. It makes life easy. That's the first thing. So that rectangle width, which again, as we saw, is measured along the x-axis, we're going to call that, no surprise, delta x. Okay, that's the first thing. The second thing is the way I've set this problem up, I said let's use 4 rectangles. You can use 2, you can use 4. We're just doing one beginning example. Okay. So next, we have, as we said before, we have to choose which y value we're going to use. So for our purposes, I'm always going to choose the y value that's on the left end. Now, as we just indicated, you could use different y value. You could use the y value on the right, a different y value, something. For our purposes, we're going to just always choose the one on the left. Okay. So the area is approximately the sum of the rectangle areas. So let's figure out what those rectangle areas are. So so what is the height of the first rectangle? Why is it 1? Right, because the first rectangle goes from 1 to 1.5. We said we're using the leftmost x value, so that's 1. So that function value is just 1 squared, so it's 1. Okay? And what's the width of that rectangle? 0.5. Okay. Rectangle number 2. For rectangle number 2, there's the base. What's the width? 0.5. They all have width 0.5. So that's one punchline. Okay. Now what's the height of that rectangle going to be? It's whatever the y value is. So we're using the leftmost x, which is 1.5. So what's the y value? Well, you got to square 1.5. You get 2.25. Okay. So long story short, here's the picture with the rectangle tops indicated, and there's how you're going to write out the calculation. So the first rectangle, there's the height, there's the width, multiply, get the area. Second rectangle, there's the height, there's the width, multiply to get the area. Third rectangle, fourth rectangle, etc. Okay. So first of all, does that make sense? So we've got a bunch of rectangles. We're saying the area in those rectangles is approximately the area under the curve. Okay. So 2 things. First of all, to come to the comment before, this method of approximating area actually originates with Archimedes and the ancient Greeks. So we kind of know where this is going. This has something to do with doing integrals. So that's how long people of human civilization have been thinking about how do we actually calculate an integral. So yes. Okay, so that's the first thing. Okay. So, all right, I wrote you do here, but I think I'm gonna go through this with you guys just to save some time. Okay. So here we've got a new function. F of x equals 0.5 x squared plus 1. And let's approximate the area under that graph, going from x equals 2 to x equals 4, and use 4 rectangles. Okay. Okay. So always the first thing when you're doing, the first thing to figure out is what's your delta x. Because that's going to tell you, first of all, your width, and that's going to help you find out what all your middle x values are. Okay. So if the width is 0.5, then your first, let's see, so what's your first height going to be? Your first height, well, your first x value is 2, so the height will be f of 2. The next x value is 2.5, so the height of the second rectangle will be f of 2.5, et cetera, et cetera, et cetera.
Which is the width, or you're going to get this, or we have to do something particular to choose the width, like 0.5?
Oh, okay. Well, okay, so notice in the question it said use 4 rectangles. So you actually calculate the width, because you know you're going from 2 to 4. So you're trying to travel 2 along the x-axis, but you're doing it in 4 rectangles, so 2 over 4 is half. So the width is something that you calculate from what's given. Yeah. Okay. So then if you actually do these calculations, you figure out f of 2, f of 2.5, blah, blah, blah. Delta x is always 0.5. Just plug it in, calculate, you get that approximation. Okay. So, yeah, Paul.
But those points are like outside the curve. When you say approximate the area under the curve, like, can we have?
Well, okay, so the picture, so to go back to the previous problem, because I have the graph, this is the picture. So let me fill in the picture by actually filling in the rectangles. So the first rectangle is this. Second rectangle, third rectangle, and the fourth rectangle. So so when we're doing this approximation, what we're actually calculating is the area of these rectangles.
Yeah, right.
And it's sort of an approximation for the area under the curve, but in this particular picture we can see that stuff is missing. Okay, so we're going to start to worry about that in a second, but just not yet. Or we're just going to be, I should say, we know that stuff is missing, we're going to solve that problem in a second. Does that make sense? Okay.
So like the one that we calculated, that one's like the outside of the curve? Or
Which one?
The one which is not missing.
I mean, the one that we just calculated.
This one?
The one with the graph.
With the graph. Oh, so when you actually, so I didn't even fill in the numbers there. Oh, yes, I did. Sorry. If you fill in the numbers, you get 6.75. So the area of the rectangle is a 6.75.
I mean, is that the area under the curve or like outside the curve?
Is
It's
it
the-
overestimated or underestimated?
It's the area in the rectangles. So it's the area in the rectangles. So you tell me, is 6.75 too high or too low? It's too low because there are these little things that we're missing. So it's an approximation, but by looking at the graph, we can tell our approximation is too small. Is that your question? Okay. All right. So I want to now start solving this problem. Okay. So first of all, so what is this called that we're calculating? So we're using rectangles to approximate the area. And remember, I specified that for our purposes, we're always going to use the left endpoint on each interval to find the height of the rectangle. So this is called the left sum. And the notation is L, big L, little n, sub n. L, because we're using left endpoints, and n is the number of rectangles. So for example, what we just, if you look at the picture, what we calculated for that function was L4. Okay. So now the big question. Clearly we've made an approximation, but it's not as good as we'd like it. How can we make a better approximation?
Rectangle smaller.
Right. So you could say this one of two ways. As you said, you could make the rectangles, well, narrower. So making the rectangle narrower is the same as saying, give me more rectangles. Okay. Super. Now, if we want the exact answer of exactly what is the area, what do we have to do?
Take it. The limit should be.
We have to take the limit. You want delta x to be smaller and smaller and smaller and smaller and smaller. And I think I could sort of draw the picture, but is anyone in here not convinced that taking delta x smaller and smaller and smaller is going to give you these skinny rectangles which approximate better and better and better and better the area that you want? Does everybody believe that?
Yeah.
Does anybody not believe that? This side is quiet. Do you guys believe that? Okay. So, just to, I guess, illustrate the point a little better, let's go back to this picture. So what I could do is I could add in these rectangles. So now I'm going to, instead of having 4 rectangles, I'm going to have 8 rectangles. So now my areas, so now the area of the rectangles will look like this. And is that a better approximation?
Yeah.
Okay. So by making the rectangles skinnier, you can see that we're clearly including more of the area under the curve, and there's less that's not accounted for. And so as you have more rectangles and you make your delta x smaller and smaller, you get closer and closer to the rectangles being the actual area under the curve. And as we can imagine from all the calculus that we've seen before, if you take the limit as delta x goes to 0, you get super, super skinny rectangles, and it becomes in the limit exactly the area. Okay. So, what do we have? Well, initially we had an approximation where we said the area was approximately, if you remember this notation, the sum of, now how do we find the area of each rectangle? It was the height, which was f of x, times the width, which was delta x. And we add them all up, so it was sigma for sum. Okay, well now what? We just said we're going to take delta x all the way small. In other words, the limit is delta x goes to 0. Well, what happens to this expression when you take delta x all the way small and you take the limit? What does this become?
Integral.
This is an integral. We've done this before, where we had the sum of some function times delta x, and we say let's take delta x smaller and smaller and smaller. We already did that.
Euler.
We did that in the Euler approximations.
We have another name for that too, like Riemann.
Yes. So now we know that we can find the area by using an integral, and we're going to integrate from a to b. A is the first x value, and b is the stopping x value. And just to make sure everybody remembers that we have in fact done this before, let me flip back, and there we go. Okay. Right, this was this. We said this is like the first fundamental theorem of calculus. We said we're adding up, it was f prime of the values times delta x, take the sum, and then that gives us the original function. The only difference is now, instead of saying we're starting with f prime and we're getting f, we're starting with f. But either way, it doesn't matter. This goes back to understanding the relationship. We know that all we want to do is take an integral, and we know how to take an integral.
Question. If our segment A to B is not continuous, say there's an asymptote, how would we know, because we don't know the original function? So technically, I guess maybe the domain of the integral.
Where are we? Good question. You are 5 minutes ahead of me. So, if you can hang on for 5 minutes, I'm going to talk about that particular problem. Okay. So, here we go. So here we have a function, f of x equals 2x. I want to find the area under it between x equals 3 and x equals 5.
So it's integral of 2x from
5 minus 9.
3 to 5.
Yeah.
16.
Right. So the area is just the integral. Right. So the integral of 2x is x squared. So you want x squared evaluated from 3 to 5. So you get 5 squared minus 3 squared, which is 16. So the area is 16. So it's now that we know what we know, that we can find areas using integrals, it's that easy. Okay. So the procedure is easy, but understanding why it works can be hard, but it's important to understand why it works so we can use it properly. So as I said before, this is, on one hand, this is a different way to understand what an integral is. And on the other hand, this is sort of like the simplest application. This is a very simple application of integrals. Later on, we're going to do much more complicated applications of integrals. And it's very useful to simultaneously understand this about an integral. On the one hand, it finds an exact area. But on the other hand, an integral comes from doing an approximation of the area using rectangles. So if you can remember both of those simultaneously, that's going to help us in the future with more complicated problems. So remember both of those things. Even though it seems like, oh, integral area, boom, 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 remember both of those things. It will be helpful. Okay. So about this one. The function is e to the x. Let's find the area under that function from x equals 0 to x equals 4. Right. So why is this one easy? What do we have to do? Right. Why do we just plug it in? Right. Because the integral of e to the x is right. So this is an easy one. Okay. Next, what is the area? So here's another function. What is the area under f of x equals sine x between 0 and 2 pi? Well, let's take a look. So the area should be the integral from 0 to 2 pi of sine x. Now, what's the antiderivative of sine? Check it. Negative cosine. Because the derivative of negative cosine is sine. So always check that. Okay. So negative cosine from 0 to 2 pi. Now what happens when we plug in these values and evaluate it? Yeah. You get negative 1 plus 1, which is 0. Okay. So how is it that the area, so here's sine, here's a graph of sine from 0 to 2 pi. How can it be that the area is 0? What does that mean? Why do they cancel?
The area of the area above the curve is in a negative.
Below is below the curve.
No,
Right.
but in that case, it will be above the curve.
Yes. Okay. Above the curve, below the axis.
Below the
Right.
axis.
So remember how we describe what the area is. We said it's the value of the function times the width. So okay, well, what does that mean about this area? Here, over here, the function values are positive.
Right.
So you're going to get positive numbers.
Over here, it's going to be negative.
But what about down here?
The rectangles are going to be
Right, we got negative function values. So in effect, everything down here counts negatively. So when we talk about finding area using integrals, we have to be careful. We have to remember what we mean by that. So, and this is,
Can we take it as an absolute value?
there you go. So we think of area above the axis, above the x-axis is positive, area under the x-axis is negative, and this is what is called signed area. Sign SIGN, like positive, negative. So integrals actually calculate signed area, not just area. Does that make sense? Okay. So you can have something like the integral being 0 because we think of this one area being positive, the other area being negative, and we know by the symmetry of the sign function that those two things are equal, so they cancel.
So how would you approach it if you want to know?
Divide it into two.
Good question. So if you wanted the area,
Would be absolute value?
so first of all, right, so 2 ways to do this. Number one, you could say, I'm going to integrate the absolute value of sine. So that would give you the actual area in terms of, if you like, square footage. So that's a very good point. That's one way to do it. And someone else was saying something else clever. What's another way to do
You
this?
bound it by a constraint from 0 to pi and multiply it by 2.
Right. From knowing this function, we know something about it. We know that the area bounded from 0 to pi is the same as the area bounded from pi to 2 pi, just that one's on the plus and one's on the negative.
But that is limited.
So what we could do is we could just find the area from 0 to pi and then double it, because we're clever.
That way it's limited though. What if our segment is a lot bigger?
Right. So that's obviously a special trick you can only use for functions with symmetry. If your function does not have symmetry, you in effect have to do what Gabriel said, which is integrate the absolute value. Now, how would you integrate the absolute value of a function? Well, what does it mean? Well, what that means is, I'll apply it to this case. From 0 to pi, you integrate sine x. But what about from pi to 2 pi? You would have to integrate negative sine x, because that's what absolute value does there. Absolute value says I'm going to put a negative in front, and that's going to turn my negative values into positive values. So you'd have to set up separate integrals on every range. So one integral over the range where it's positive, you find that area. Another integral over the range where it's negative, but you put a negative in front to make all the values positive. So I didn't want to get into that yet, but that's a really good question. You pushed me forward. So generally, we're not gonna worry too much about that. Okay. But it is important to understand positive, negative area that we're going to think about all the time. Yeah.
So now we don't ever have to approximate using rectangles again, right? Thank God.
Maybe just once or twice, just to make sure that you've got the idea. Okay. All right. But now we do come to another tricky case. So the integral of x to the negative 2 from negative 3 to 2. Okay. So let's pretend I didn't put the words tricky case above this, and let's just do this problem. So if we just do this problem, what happens? Well, what's the integral of x to the negative 2? Remember that it's x to the negative 1 over negative 1. So you just write that as negative x to the negative 1. Evaluated from negative 3 to 2. And that gives you, let's see, if I plug in 2, I get negative 2 to the negative 1 minus a negative 3 to the negative 1. So this is negative a half plus a third. So that's just negative 1/6. Okay. So if I just did this using standard techniques, I would get negative 1/6. Okay, great. What's the problem? Problem is this is wrong. Why?
Area is not can be negative.
Area can be negative.
No, it's signed
One
area
sec.
anyway.
Yeah, it's signed area.
Okay.
It could be. Well, it's not because to the negative, the curve should still be above our axis.
Right. So x to the negative 2 is the same as 1 over x squared. So what do we know about the values of 1 over x squared? They're always positive. So how can I say a function that's always positive, and I calculate the area, and I get a negative number? That doesn't make any sense. So what's the problem?
It doesn't exist. It doesn't.
You have unlimited area.
You have unlimited area. Right. And precisely where is that problem?
The function doesn't exist as a domain.
Where is that?
Zero.
At x equals 0, there's a problem. The problem is that the function is not defined. So how can you calculate, how can you operate on a function that's not defined? Right. We skip that. Okay. So, and that's the problem, is we're trying to go from negative 3 to 2. So we're including this place at x equals 0 where the function is undefined, it's infinite, whatever. So you can't do that. And when you try to do that, you get a nonsense answer like this.
But you can split the function and sum.
But even if we.
Okay. So how to deal with this exactly, we're actually going to come back and talk about it later in the semester. So for now, so we're already starting to do integrals. So I just want to point out the fact that you have to be careful because sometimes annoying things like this happen. So how to deal with this is kind of advanced, and we'll think about how to deal with this later in the semester. But for now, I just want to alert you to the problem.
Have to know boundaries when it approaches infinity. Like
We're going to do fancy stuff. We'll get to it later.
so if you're not going to give us a question like that to trick us on the exam? If you do, what do we have to do to find out the domain of our original?
Right. So what do we say about this integral? The integral is undefined. Because you can't talk about function values from negative 3 to 2. Because at 0 it's undefined. Function undefined at 0, so the integral is undefined at 0. But it's undefined because it includes 0. I should say it that way. So the answer is undefined. Is that straight? So one trick with integrals using area. So as I mentioned before, we're only starting to learn about different things that we can take the integral of, that we know how to take the integral of. There are lots of functions we don't know how to take the integral of. But we're about to expand our repertoire by 1 or 2 functions by using a nice little trick. So what if I say, what is the integral from, let's say 0 to 3 of the square root of 9 minus x squared dx? First of all, is this a function that just by looking at it we know how to take the antiderivative of this? This is not. Okay. However, we're going to do this integral by thinking of it in terms of area. So, what is the graph of this look like? Yeah, if your function is y equals the square root of 9 minus x squared, what does that look like when you graph it? Okay. So in order to do this question, you need to know something about these equations. Okay? So just to finish this out, I'm going to solve this. So, not solve it, I'm going to rewrite this. Square both sides. Bring the x to the other side, what do you get? X squared plus y squared equals 9. What is this? It's a circle. It's a circle with, where's the center, where's the radius? That's right. The center is 0, 0, and the radius is 3. Okay. But the original formula, is it the entire circle? No. Only the positive half, because first of all, it's a function, and second of all, that's how we define square roots. So, 1, 2, there's 3. There's negative 3, and the best I can do is something like that. And we'll just pretend that's half a circle. Okay. So, that's our original function, and we're trying to integrate from 0 to 3. Well, integrating from 0 to 3, as we just learned, is the same as, let's find the area under the curve. In fact, Paul, that's the exact point that you were making. Only here, we're going to use that fact to our advantage. Because doing this integral is the same as finding that area. But, what's that area?
Quarter of the circle.
Quarter of the circle. So the integral equals 1/4 of the area of a circle. Or this circle. And what is the area of this circle? Pi r squared. And what's r?
3.
So there you go. That's the answer. So this is, like I said, this is a trick, and you should think of this as one of the last tricks in your goodie bag, as far as thinking about how do I take the integral, or in this case, how do I take a definite integral of something? You should say, is this a function that I know? And then if not, this is the only trick that you have at this point. We're going to be learning more going forward.
No, that's the answer.
9/4 is the answer. The whole point is that we don't actually have to use algebraic techniques to solve this, because we can use geometric techniques to solve this. We simply say it's the area, and we know what the area is. It's slick. So that's one trick. Any questions? Yeah.
What if you added a constant to that equation, like +5 or +6?
Oh, good question. You mean like in the homework? Okay. So, follow up. What about from 0 to 3? Okay, so how do we do this? You can, I'm sorry? What do you mean? Exactly. This is the same as the integral from 0 to 3, the square root of 9 minus x squared dx, plus the integral from 0 to 3 of 4 dx. Because what do we, and this rule, if you like, think of it as coming from derivatives. With derivatives, when you have something plus something, to take the derivative, you just look at each term individually. So you can do the exact same thing with integrals. And now we know how to do both of those integrals very quick.
The second part is going to be 4x.
Okay. Sorry? Yeah. Okay. That's straight? Okay.
Can we do another example like?
This is basically this is just about the only one that we're going to have to worry about or think about. There are other equations where I could teach you how to do it, but basically the circle is the main one that we're going to look at. Okay. Right. Okay. That's that. Next. All right.